Judge, who will tell us about systoles and translation surfaces.
Thanks very much. Thanks to the organizers for the opportunity. So I'm going to do something very static, sort of out of context. I'm going to do a static problem. It doesn't have any dynamical parts to it. It doesn't have sort of a Markov chain. It doesn't have a SL2R action. It's basically just geometry. But the geometry of translation surfaces, right? So, and one translation surface at a time. We're going to talk about systoles. So first I'll tell you what a systole is. Talk about hyperbolic metrics and more general metrics where it's been studied a lot with mixed success. Then we'll move on to translation surfaces, and I'll give you some results about systoles for maximum systolic ratio for minimal strata, and then the maximum systolic ratio for H11, which at this point is still conjectural, and then talk about the maximum number of homotopy classes of systoles in a surface in H11, and then some other results. Okay, so what is a systole? So just take a length space associated to some metric D, and look for take noncontractible loops. So these are not base loops, just take any loops. Take the infimum of the shortest, or the infimum of the length of those, so the shortest if it's realized, and that's a systole. Okay? So a systole is something which realizes the infimum of the shortest non-contractible curve. So if you like dynamics, it's sort of the shortest closed trajectory. Okay, so the systole is really important as in terms of moduli space. So let's assume we have a compact surface. We have the moduli space of hyperbolic metrics on that surface, isometry classes of hyperbolic metrics, a finite dimensional space, and Mumford, extending Mahler's work on just lattices, showed that 1 over the systole is a proper function, meaning that as you go out to the ends of moduli space, the systole goes to 0, and 1 over that, of course, goes to infinity. So it's a proper function. What we're interested in this talk is sort of the opposite. Instead of going out to infinity in moduli space, let's look at the middle of moduli space. So going out to ends of moduli space in the hyperbolic world means pinching a short geodesic, or the systole. And so making these very long cusps. And we'd like to look at the other extreme where the 1 over sys of xd is actually minimized. That is, that sys of xd is maximized. So we want to look at the maximum systolic ratio over the moduli space. You can think of these as the fattest metrics. Right? It's a notion of fatness. So we're looking for the fattest metrics, if that's a PC term, or I don't know. But so.
Why are you calling it a ratio? It's just a systole. Where's the ratio?
Did I say ratio here?
Yeah.
Where did I say ratio?
Systolic ratio. Okay.
Oh, I say systolic ratio before. Well, okay, so yes, the point is for hyperbolic metrics, hyperbolic means curvature minus 1, so it tells you that the volume is a fixed constant, independent of the metric, right? But if I look on translation surfaces, I could always rescale them. So if you like, systolic ratio is basically systole, where you've normalized the measure of the surface, measure of your space to be 1. Yeah. I'll talk about that. But in hyperbolic surfaces, it's simpler just to talk about systoles. Okay, so hyperbolic metrics on surfaces, hyperbolic metrics on genus 2 surface, it's known that there is a fattest surface, and in fact it's the unique fattest surface. So there's unique maximum. It's called the Bolsa surface, and it's probably a surface that you've thought about yourself, just playing around with hyperbolic geometry. So you identify opposite edges of this octagon. This is a hyperbolic octagon. I get to choose, it's a regular hyperbolic octagon. I get to choose the angles at the vertices. I choose them all to be the same and equal to b pi over 4. You identify opposite sides, and because of the pi over 4 condition, you get a smooth point after making the identification. So this is a smooth hyperbolic surface. And this guy has the unique maximum for the systole. It has the it's the fattest of all the genus 2 surfaces. Genus 3, we don't know. Schaller or Schmutz, depending on what year you start looking at his papers, has some conjecture about what should happen in genus 3, but we don't know what the fattest surface is for genus 3 or even above. Okay, so that we just stopped at genus 2, and genus 2 is 1984. Notice that this Bolsa surface also maximizes the isometry group, has the largest isometry group. It's not the Hurwitz bound, it's half of it. So, but it still maximizes. Okay, then you can say, okay, hyperbolic metrics are nice, but what about all metrics? And sort of, this is something that was thought about by some, I think, after Levner, Berger, and then Berger got Gromov interested in it, and there have been a lot of people who've worked on this consider. But all metrics is no good unless you have something to normalize, because I can always just expand the metric. So to normalize, I need something like a volume. And so one way to make this look nice is you just restrict to a manifold with a Riemannian metric, say, and you take the systolic ratio, you raise it to the nth power. If it's an n manifold, divide by the measure. This makes it homogeneous of degree 0. It's homogeneous function of degree 0, so when I rescale, I see nothing. Or if you like, more practical, just choose your metrics to have area or volume 1. But that's a systolic ratio, that thing there. And this is the answer to Barak's question. For hyperbolic surfaces, this is a constant, so you really don't have to worry about dividing out. Okay, so what is known in that setting for genus 2, general metrics in genus 2 is the maximum systolic ratio. Well, it's unknown. It's genus 2, no one knows if I just give you an arbitrary metric. And even is it achieved? For hyperbolic metrics, we know, because it's a proper function, 1 over the sys has a minimum.
Chris, what was the, sorry, at the end of the last slide, I just missed the very last thing.
Oh.
Just going a bit fast.
Sorry. Okay, yeah, please, am I going too fast in general? No? Okay, please tell me. Because it's easy to flip through slides, and the tendency is just flip, 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 flip. So please stop me if you, thank you, Saul. Okay. Right. So is it achieved? Gromov has a sketch of a proof in his filling manifolds paper, which tells us that it's achieved for so-called generalized metrics, which are basically sort of L2-like. They come from taking limits in L2 of conformal factors. Everything is conformally equivalent to some surface, some constant curvature surface, and you take those conformal factors, you take the limit, all possible limits in L2 of those, and so he has a notion of generalized metric, and the claim is that it is true in that case, but Calabi has work that indicates that in fact you should see cone points, you should see singularities. And it was thought for a while, including Berger, that what you should see, a possible maximum among all metrics so I'm going outside the Riemannian context, but slightly, is that you should see flat metrics with cone singularities, cone point singularities. Saburo, okay, he's in Paris. He proved that, in fact, you have to have some positive curvature for this. So it can't be just flat metrics with conical singularities. Nonetheless, it's believed you still should have some conical singularities. Not necessarily multiples of 2 pi, but they do come up. And so that should be gratifying to those of you who like conical singularities, that they sort of naturally come up in extremal problems. If you restrict to just cat0 metrics, so non-positive curvature, then you can achieve in genus 2, you can achieve the maximum systolic ratio with a flat Bolsa surface with conical singularities. The reason I call it Bolsa is because it's conformally equivalent to the Bolsa surface. It's still in the same conformal class. Bolsa surface really is defined by algebraic equations. And it has a nice picture. There's 8 regular octagons centered at the Weierstrass points. We're in genus 2, so we have 6 Weierstrass points. So that's sort of the picture for general metrics. I just wanted to point this out for context.
6 regular octagons?
Oh, sorry. No, it should be 6 regular octagons. You're right. I don't know why I wrote 8. I guess I wrote 8 because 8 is octagon. OK, yeah, thank you, Saul. Very good. Yeah, 8 is not equal to 6. Right. OK. All of this business goes back to the first result in this direction was due to Levner, who actually is my great-great-grand advisor. So I feel necessary to pay tribute to Levner, which everyone does. So if you just look at genus 1 and you look at all Riemannian metrics, then the systolic ratio is maximized for the hexagonal flat torus. Okay, so that was the first. He actually didn't publish it. It's actually mentioned in his student's thesis, and a student does it for some other small complexity surfaces like the projective plane, et cetera. But he never actually put a proof in. But based on his student's thesis, one can try to look at the argument. So this is a pretty long slide. I'm just going to run over it. One of the reasons I'm going to run over it is sort of this final step is where we got started in our project, is trying to understand a good proof for that. I'm not sure it's his proof. Based on Pooh, I think the first part is Levner's argument. And it also shows what goes wrong in higher genus, this proof. So it's not so bad. So let's take a metric G, Riemannian metric on a flat torus. We can uniformize, meaning we can write it locally as rho squared times dz squared, where dz is the natural holomorphic 1 form on a flat torus C modulo lambda. Lambda is the lattice. Right? So you can think of the torus as a group. It's a group, and it acts transitively on self. So that's a nice thing. And you can average the length element, this rho, well, not rho squared, but rather rho, over the torus. And when you do this, the average, you can check the average has larger systole. There's some little computation. Look at the video later if you want to try to understand the computation. And the average has smaller area, and that's just the Cauchy-Schwarz lemma. Okay, so by averaging, you're going to increase the systolic ratio because you're increasing the length and decreasing the area. And by that I mean non-decreasing or non-increasing, right? So since it's a transitive action, the average is constant. Okay, so that's it. You know that you have, this guy must be a flat, well, it's not it quite. You know this guy has to be a flat torus with rho equal to some constant. We have flat torus, right? Okay, so that's the analysis part to get rid of the conformal factor. And then the final step is to show that the hexagonal metric is maximum along flat metrics. So we reduce ourselves to a flat metric problem.
Wait, can you explain next to the last step? Why is it? Where do you use transitivity of the action? You've shown
Well, I want to show it's a constant. So I'm averaging.
the average is already so.
No, average it. So rho is a function. So I have this function,
Right.
and I'm going to average it over the entire surface. So if I just take it, if I just don't have transitive, I just have two elements in my isometry group, and I just take this plus that, it's not a constant function. The sum of two functions is not going to be constant. But if I have this action, it smooths out everything. It becomes a constant.
Wait, you average it. The average isn't the average a number? Oh, it's the average length on it.
It's the average length element. Yes, this is it. Yeah, it's not a number. It's a right. It's this integral. This rho depends on x. T here is in the group. So for every x, so there's an actual function of x here. Function of x, function of x. Yeah. Thank you. Very good question. Yeah, I should have put the x's in. Okay, so the final step is the hexagonal metric is maximum among flat metrics. Okay, so let's look at that. And this is what.
So, Chris,
Oh, sure.
The original space is just tori of area 1, but not flat, just whatever.
Right. You could use area 1. Not even. Yeah, if you like area 1. Yeah. Actually, for this argument, you really don't want area 1 because, yeah, you're an averaging doesn't preserve. So you really want, it's nice to divide out by the area. Yeah, you're welcome. So, okay, so let's go to flat world. And how do you solve this problem? Gromov actually in his book says, yeah, this is just an easy problem. And it is an easy problem, but it's a nice method. And in fact, the way we'd like to do it, Hugo and I, is to use basically Fayes-Toth's lemma, which is the thing that gives you that the hexagonal packing is the tightest circle packing in the plane. Okay, so this nice lemma that he uses in his, you find it in his regular figures book. First, let's look at the reduction to that lemma. So let R of t be the injectivity radius of the torus. So you're given a flat torus, injectivity radius. So it's sort of the largest ball you can embed inside the torus. Okay, that's how you should think of it. And then consider the Delaunay triangulation with respect to the point z naught. So here's z naught, and I've drawn the ball. It doesn't matter where I center that ball because it's translation invariant, this metric. So for injectivity radius purposes, I just fix z naught. I look at the Delaunay triangulation. Remember, does everyone know what the Delaunay triangulation is? There must have been a course about this, right? No? There was no course? So, okay. Why? Why, John? Okay. So the Delaunay triangulation is you take the Voronoi decompositions, that is, look at all the points that are closest to your cone points, to a given cone point, closer than any other cone points. That decomposes you into little cells, basically neighborhoods of your cone points. And then there's a dual to that. And that dual cell decomposition is called the Delaunay. And so this is the Delaunay for that. So this is the Delaunay for z naught. So I have two cells in this case. Yeah, that's bad. I thought someone would have talked about this in the summer school. Okay, so here's my torus. I want to make the systolic ratio better. Well, one thing I notice is each systole is parallel to a Delaunay edge with length 2r. That is, if I have any systole here, this is just a fact about Delaunay, it contains the shortest edges. It's a very nice fact about Delaunay. So, in fact, you can see the shortest loops are this one and maybe this. Oh, not even that one. These two, I guess, might be short. This one might be the shortest loop here. this one is longer. Notice this distance is r, that distance is r, this length is 2r, but this is going to be bigger. So in fact, the systole here is just this guy. And it's where that ball butts up against itself. That's where you get the shortest guy. Okay, to make it shorter, what you do is you want to push everything so the ball butts up to itself 3 times. And that's this picture. Okay, and this has got better systolic ratio. And this is the basic lemma that tells you this is true. If I take one of these triangles, and I look at the sort of largest ball centered at all 3 vertices simultaneously that embeds inside that triangle, and I take the radius squared, oops, that's not what I want to do. Take the radius squared and divide by the area. So the radius squared is a measure of area. It's a measure of area here. So it's basically a measure of these 3 areas. And if I divide by the area of the entire triangle, that's maximized if and only if I have a configuration like this, where I have the ball kisses itself 3 times. So this is the best. And this is an equilateral triangle. So in fact, what it just says is in order to make your surface have the maximum systolic ratio is that you should be tiled by equilateral triangles. And that means you have the hexagonal torus. Hexagonal torus, when you do the Delaunay triangulation, it's the one that has both of its Delaunay cells are equilateral triangles. Yeah?
So what are in the picture the Voronoi cells?
Right, so the Voronoi cells here, so yeah, maybe it's better to draw it here. Yeah. So what you do is you start with these guys. So you start with this, and then I draw the equidistant line like that. Here I draw the equidistant line here.
So you consider them as different points. So you're not
Right, I consider these as different points, exactly, yeah.
and so why is that diagonal edge?
So then I'm not doing a very good picture, but it's something like this. So this actually, this should be equidistant. This line should be the equidistant between those 2. Yeah, yeah. So that's the Delaunay. Anybody want to know more about Delaunay? Delaunay is again the cells here. You look at for all the points that are closer to this point than to this point, or this point or that point. And here you look at all the points which are closer to this point than any of the other 3 points. And for this point, you look at, okay, so that will give you the Voronoi, and then you look at the dual graph. So the dual graph is I connect 2 vertices if the 2 cells containing them share a boundary, an edge boundary. So I get this, right? And then I get this, and I get this, and I get this, and I get this, because I'm dual here at these places. Okay. That only took like 2 minutes, John. Okay. So systolic ratios on strata. So let's go to strata. Let's go. Oh gosh. Okay. Yeah. Right. Oh, I started 2:17, 18. Okay. Thank you. I watched that. So systolic ratios on strata. So let's move to strata, which I guess we're all interested in, hopefully. You know, we have a holomorphic 1 form. Here is the length element, right? I'm going to take the infimum over all non-contractible closed curves, and I will divide by this. Now, of course, these shortest curves may not be cylinder curves. Like in Alex's talk, they may be curves of a different type. So we're allowing for crooked curves, curves that are not bounding a cylinder or in the middle of a cylinder. Okay. And so all homotopy classes of curves. And the question is, what's the maximum systolic ratio for a given stratum? Okay, so minimal strata.
Just sorry.
So,
Okay, fine. Sorry.
no problem. Minimal strata. So we realized very quickly that for minimal strata, basically the Fayes-Toth argument works. So remember, a minimal stratum is one where you just have 1 0 of whatever multiplicity it has to have on a genus G surface. And basically what you do again is you just take the del and A triangulation, and you notice that, well, because you only have, basically every homotopy class of curve can be pushed to a cone point, and so you only have to look at the ones that go through the 0 or the cone point, right? So if they're not, and then you look at the del and A partition, and you can increase your systolic ratio by using by pushing your triangles more and more equilateral. The same argument that I use for the torus works here. What's important is that we only have 1 0, so every systole has to go through that 0 and only once, and it consists of just one single del and A edge. One single del and A edge. In other strata, that systole might consist of many del and A edges. Not just del and A edges, but it might consist of many saddle connections. So it may consist of other saddle connections, more than one saddle connection. Here, it's just one saddle connection that works for everything, because we only have 1 0. So the Fayes-Toth argument breaks down because of that. I mean, Fayes-Toth lemma is perfectly good, but it just doesn't apply in more general strata. More general strata, you have to work harder. So it does work, however, if you're willing to look at the relative systolic ratio or the relative systole. So the relative systole would be a very natural, from the point of view of strata, you take just the length of the shortest saddle connection. Okay, it comes up all the time in this business. And the 1 over the length of the shortest saddle connection gives you a proper functional moduli space, which is a very useful thing. On a given stratum, very useful thing. And the Fayes-Toth argument does work for this relative notion. So if you're just interested in the length of the shortest saddle connection, then you can see that the maximum has to occur if you have equilateral triangles in your del and A triangulation. Bossi and Janinska have an independent proof of that for the relative part. So they have a relative, but so we saw this Fayes-Toth argument because we've been thinking about a problem in hyperbolic geometry, but we saw this and we said, wow, this is easy. We just have to figure out how to apply this all the time, and we can get all strata. And yeah, no. This was like day 1, and then now we're on day 1200 or 1500 and something. And the stratum H11, we still don't know. For stratum H11, so that's the next simplest stratum, and this should be the next simplest stratum. Here's our conjectural maximum. We think this is the surface. We identify the colored edges, right? So this is a translation surface. The holomorphic one form is dz, as usual, in the plane. And here, this surface is determined by there's a circle here. I don't know if you can see it. There's a circle there, and these are circumscribed by, these polygons are circumscribed by those circles. And this edge length is 1, and that edge length is 2. That determines the entire picture. It's not a regular hexagon on either side. It's a little twisted from a regular hexagon. And we conjecture this has the unique maximum. So so we spent a lot of time trying to, so we have partial things that tell us in this case, yes, in that case, yes. But it's like this big, it's a nasty optimization problem because you're dealing with a space which has got many different corners and edges, and you actually have a quadratic functional or a ratio of two quadratic forms. So it's kind of a mess. So we don't know that this is.
Do we need to know the radius of the circle, or?
No, because it's a systolic ratio, so if I rescale. Oh, yeah, sorry. Do I need to know the ratio of the circle? That's a good question. No, I think it's determined by this. I've forgotten it's a good question.
So it's like area 1 or something like that.
I've forgotten what it is. Yeah, that's a good question. I think it's this just enough to have the 1 and the 2, and you know the rest. Am I right? I don't know. Okay. Sorry. I don't remember offhand. Okay. Systolic ratio, we know the systolic ratio is this for this, and it's about 0.8404, and we just can't find anything that does better than that. And we have reasons to believe that it actually is that. Other critical points of the functional, all the other critical points we can find all have systolic ratio less than 1 over square root of 3, which is pretty darn close. These are the ones related to the hexagons. This is related to the systolic ratio of say, the hexagonal torus. Okay, it has, but this one's a little bit better than all the others. Yeah.
By curiosity, this one belongs to the remultiplication lattice?
This one. Good question. You're asking, does this belong to? I know that it's not Veitch.
Yeah, of course, in the neutron one you cannot.
Of course not. Okay. Okay. But I don't know. It may belong to the real multiplication locus. I haven't thought about it. It's a good question. Yeah. Yeah, one of the things I was disappointed by, I was hoping you would get Veitch surfaces out of this or something, that you take extrema, you should see nice surfaces. In this case, you didn't, so. Or lattice property, not Veitch, lattice property. Okay, so, okay, so let's go to, so I don't know how to do this. And that's where we're stuck. And maybe if someone shows interest, maybe we'll try to figure it out again. So then we thought, that, of course, if you can't solve a problem, you should change the problem, try to find a simpler problem to work on. And so Hugo suggested, okay, let's try to find upper bounds on the number of systoles, which is also something in the systolic world they are interested in. So how many systoles can and in this case, well, first observation, if a metric is smooth, then two systoles can intersect at most once. Okay, because if you start with 2 and they intersect here and here, then you can take this, you can cut along this point and this point to get 4 arcs, and you can look for, among those 4, the shortest of those 4. And then you can, because this is a smooth point, you can make a small perturbation. And the angle at which those things, it's a transverse intersection necessarily, so the angle is not pi. So you can cut off a little corner and save a little bit of length. So by doing a small perturbation, you can make a smaller thing. So this is a proof by contradiction that a systole cannot intersect another systole twice or more.
Why is it not null homotopic?
Why is it not null homotopic? Which is not null? This one is null homotopic. Okay. Yeah. Yeah. Okay. So I'm always thinking in the non-positive curvature world. There's a number of upper bounds in the non-positive world. So let's assume our metrics are non-positive. Because for me, I'm always thinking either about translation surfaces or hyperbolic surfaces. And in the case of either one of those, there's the bygone lemma, which tells you this couldn't be, there's a bygone, so you can't have a bygone inside a non-positively curved thing. Okay? Okay, good question. It's right. It could be, in general, it could be. But this is, I'm thinking of non-positive curvature in If you have positive curvature, it could go wrong. Okay, here is the best result for hyperbolic surfaces. It's known the genus 2 surface has at most 12 systoles, and the every genus 2 hyperbolic surface has at most 12 systoles. And the Bolsa surface is the unique surface with 12 systoles. So the Bolsa shows up again. You know, it's got that nice property again, another nice property. And this is proven by Schmidt-Schaller, but there's also, I thought I'd get rid of that typo. It should say Mellestein, Reven, and Thuron. Anyway, I hope I have the latest version of these notes. Anyway, so this is, in this paper, they have a nice argument that shows that at most 12 things can intersect at most once. That is, if you want to look at configurations of simple closed curves that intersect at most once, then you can have it, and they all have to be mutually non-homotopic, then you can have at most 12 of them. And then putting them together with this, you see that you have at most 12. Okay, flat tori have at most 3 homotopy classes of systoles. Notice I have to put in this homotopy class because, as usual, I can slide along a cylinder. So this question really for flat surfaces, upper bounds the number of systoles, well, there is no upper bound, it's infinity. But of course, we are always, in the flat world, going to talk about homotopy classes of systoles. How many homotopy classes? Okay. So here's our theorem on the number of systoles with Hugo. So an H11 surface has at most 10 homotopy classes of systoles. And this guy, this surface, which again you identify edges corresponding to colors, this guy is the unique one with 10. No other guy has 10 homotopy classes of systoles, or just, let's just say 10 systoles. Okay? And a curious thing, it's not the same as the conjectured maximum for this maximum systolic ratio, right? It's a different, in the case of the hyperbolic surfaces, the Bolsa surface served to maximize both the number of systoles, maximum number of systoles, and a maximum systolic ratio. Here we have 2 different surfaces. The systolic ratio here is 1 over the square root of 3. By the way, this is also a square tiled surface. Well, it looks like a rectangular tiled surface, so it's of each. So it's very different than the other surface. Okay, so I want to say a few things about the proof. Any questions so far? It's tiled by equilateral triangles. So there's there's this guy that sits in there, and then I've forgotten, how do you go from here? I guess, yeah, you go here, here. Yeah, you have that. Yeah. It's tiled, but it has equilateral guys. If I remember correctly, there's actually an order 3 symmetry. But please check that because I've forgotten. Okay, so how are we going to prove this theorem? How are we going to find these 10 classes of systoles? First, let me show you where the 10 systoles are on this surface, and then I'll sort of tell you how to get to this surface. So we're going to use Weierstrass points. We're in genus 2. We have the hyperelliptic involution. We have the Weierstrass points. Yeah, so we're in good shape. Okay, so here are the Weierstrass points. The hyperelliptic involution, one way to see it is just you flip 180-degree rotation around this point, right? And here are the other wires. So they look like there are more than 6, but of course this one's identified with that one, and that one's identified with this one. So you count, there's really only 6. They lie on the edges of this picture. That's why we chose this picture. So the basic lemma is each homotopy class of non-separating systoles. So look at, we're going to break up into non-separating and separating. Non-separating, guys, has unique representative. It contains exactly 2 Weierstrass points. And the proof is basically we have hyperelliptic involution. It maps, it takes all our systoles are necessarily simple closed, and it maps the simple closed, the homotopy class is simple closed, the homotopy class is simple closed curve, and but it reverses the orientation. And if you so a couple things could happen. You could have a cylinder of simple closed curves. We're going to choose the middle guy. We're going to choose that's our representative. The middle of that, the core curve of that cylinder. That cylinder is actually involuted by the hyperelliptic involution, and it has 2 fixed points. Those are the Weierstrass points. So we're looking at that core curve. That'll be one case. The other case is where the systole actually goes through the 4 pi cone points, and those 4 pi cone points are actually also involuted. So they're actually both belong to that systole. Okay, so each homotopy class has a representative that contains exactly 2 Weierstrass points. So let's see. Here are the so-called direct systoles. These are the ones that go, when I say direct, I mean they go directly between 2 Weierstrass points. Okay? They don't go into the 4 pi cone point. By the way, I should have said before, maybe it's clear here, it's an H11 surface. Here's one cone point, and here is the other one, right? So there's the diamond, which is one cone point, the open, which is the other. So the corners of our polygon are the zeros. They correspond to the zeros of our one form. Okay, so here is one systole. There is another, and there is another, there is another, there is another. There's six of these direct systoles. They go directly between Weierstrass points, don't cross the 0. And 6 homotopy classes. They all have length 2, if you look. The way we chose that original polygon, 1, square root of 3, and 2, they all have length 2. So the systole here is 2. And then for the, that's the direct ones, and then there's 4 indirect, because there's supposed to be 10 altogether, so there are 4 indirect. Here's 1. This is actually identified with that after, right? So it's just 1. There's another, oops, how did I do that? Well, it goes, right, it's in dash, sorry, I should say. It's the dashed guy.
Are the identification of the horizontal lines wrong?
No, I don't think so. So this is identified with that, and that's identified with that.
Because in the previous slide,
Oh, did I make something wrong?
Previous slide, there's no
but there is only one with this
Oh,
and
maybe I made a mistake here. So let's see. So this guy should be identified with this.
No, I mean the horizontal line.
Oh, these guys. Oh, yeah. No, you're right. There's something going on. What did I do? Sorry, I've made a mistake. This is not quite. There's another systole. Oh, it's. Sorry. Is it? It's along. No. I'm sorry. I've lost track. You're right. It's not identified with that, and so when drawing this picture, I drew the wrong thing. I promise you, there are 2 other systoles like this, but I don't see them right now, and I've forgotten what they are. So you're absolutely right. That's a mistake. So there's 2 others that go through, and where are they? Well, I don't want to think about it because I'm running out of time, but afterwards I can find them for you. Okay, so here is one non-separating. Here's another. Oops, that's the same picture. There's another non-separating. That's 2, and I think I may have. I hope I got all 4. sorry, that's one non-direct. It's indirect. So this is indirect, meaning it passes through cone points, necessarily passes through cone points. Then there's another, this is another indirect. And then there is another one, which should be, oops. Well, okay, that was another one. I think I just got 3 in there. I think I have a problem with one of my slides. That is supposed to be the different slide, but there are 4. And you can guess, they're all vertical. They're all vertical, okay? So there are 4 vertical indirect ones. And for this surface, I claim there are 10. That's the, okay.
Sorry.
Sure.
So it says that there are 4 different vertical saddle connections of length 1.
Right.
So why don't if you just take any pair of them, why don't they give you a...
Right, so, but that's what I'm doing, sort of.
So there
I'm
are-
taking, there's 4 that join the two cone points,
Yeah.
and I take this pair, that pair, this pair, that pair. So there's 2 crossing ones.
Should be 6, right? Not 4.
No, it's only 4 because you no, you only get 4. Yeah.
Maybe it's 6 this way and 4 on the previous slide. Then add up to
No. It's definitely 4 for this. It's definitely 4 for this. Yeah. Okay, but good question. I understand what you're saying, but it's only 4. That's the statement. Yeah. Okay. So yeah. Let me try to say something about the proof. Yeah. What am I thinking? So 2 distinct systoles may intersect twice at 0. So this statement is just to say that we're not in the, because we have conical singularities, we no longer have a smooth surface. What I said about smooth surfaces, that idea of just making a small deformation to reduce the length doesn't apply anymore if the intersection point occurs at a singularity. You have to take into account how big the singularity is. It really has to do with whether your 2 geodesics, when they meet at the singularity, whether the angle is less than pi or not. Okay? Nonetheless, because for separating systoles, separating simple closed curves intersect at least 4 times, using the fact that the singularity is at most 4 pi, you can show that there's at most 1 separating systole. And you can also show that there are at most 5 indirect systoles. These are the ones that may go that join Weierstrass points but may go through a 4 pi singularity, that do go through a 4 pi singularity. The hard thing that takes a lot of work is to show that the number of non-separating systoles, direct non-separating systoles is at most 6. That takes a bit of argument. Yeah, my original plan had been try to convince Hugo to try to, to sort of proselytize, to convert him into a flat surfaces person. And I think I lost him here. He doesn't. I don't think he wants to do this anymore. Okay, so using a similar type of argument, the fact that you got to have separating systoles are sort of bad. You can show that 1 separating systole means that there's at most 9 systoles. So that means if we're looking for 10, we're going to throw out those. We'll only look for the non-separating systoles. In fact, so and then so we have at most 6 direct separating systoles, and we have at most 5 indirect separating systoles. So that's 6 plus 5 is 11. So we're off by 1. So we have to do a little bit more work. So what we do is, if you have a indirect non-separating systole, you take, it goes through 2 Weierstrass points, it goes through 2 zeros, and you just cut and you get 4 arcs. And you do that for every one of the ones, all possible 5 of them you have. If one of those parts, 4 parts of a given systole is shorter than the others, then you have at most 9 systoles. And you can show that. And otherwise, all the parts have to be equal. They all have to come in equal ratios. And then by using an angle argument, the amount of angle at each 4 pi cone point, you can show there's at most 4 indirect non-separating systoles. And then so you have most 9 here, 4 plus 6 is 10. So that's sort of the thumbnail sketch of the argument. Okay. Maybe, obviously I wasn't looking at my slides. So this is, of course, in doing all this, we quotient by the involution. You work on the Riemann sphere. You have the hyperelliptic involution. You look at the quotient sphere. You have really only one 4 pi cone point. These are all angle pi cone points because you've applied the hyperelliptic involution. These are the 6 Weierstrass points. 1, 2, 3, 4, 5, 6. Or the images of the Weierstrass points in the Riemann sphere. And combinatorially, you think of the direct systoles, the 6 direct ones have to look sort of like this. And that probably is a better picture to go back and just recover my 2 missing direct systoles that I had before in that other slide. They're sort of the cycle of direct systoles if you have 6. Here's the case. These should be indirect systoles. Indirect systoles, this is the case where I have one, so here's one indirect systole. It would go in and out, and in and out, in and out, in and out, in and out. That's a 5. That's the case where I have 5 indirect systoles. Okay. To have. Yeah, sorry.
So aren't you constructing paths between distinct Weierstrass points? Or
oh, sorry. So, but that right. So once I have a path between 2 Weierstrass points, then I just lift. Yeah, I lift to the double cover, which is the original surface, and that curve gets matched up with the other side, and they make a nice big round loop. So you're right. So searching for arcs joining Weierstrass points on the sphere is equivalent to searching for closed curves on the double cover on the original surface. Okay, this is the short case, and if the distances, if all these segments are the same length, then this is the case where you can have 4 systoles. Okay, so let's go. Right. Okay, so I'm running out of time. We also do something for the minimal strata. So it's not very hard. It's the obvious thing you would do. The only tricky thing is to show that the bounds are realized. So for minimal strata, you can ask how many homotopic classes of systoles you could have. And by looking at the Delaunay triangulation, you see if you have just 1, 0, then you expect 6G minus 3 Delaunay edges. Okay. And you make everything a equilateral triangle. And you just have to show that you can realize this, and also that if you allow for hyperelliptic, then you can, hyperelliptic have to have 2 fewer systoles.
And these also maximized or not?
Yeah, these are the best. These are optimized.
Do they also maximize the systolic ratio?
Oh, for systolic ratio, yeah, everything maximizes for systolic ratio is always the same for these Delaunay guys. So there's a little difference. Some surfaces are good for the maximum systole problem, but all surfaces are good for the systolic ratio problem, as long as they have triangles which are equilateral. All the del and A triangles are equilateral. Okay, so finally, there are all kinds of questions one can ask. So the first one I was trying to get Hugo last night to remind me of the conversation we had in Lausanne maybe 3 years ago. I thought we knew that what the answer to this question was. Does either optimal surface, either the surface that we think is the maximum systolic ratio for H11, is it a Bolsa surface, or the one that has the maximal number of homotopy classes of systoles, is that in the Bolsa conformal class? I thought we knew this, but we couldn't remember what the answer was. As far as we know, it's open. So is it either one? They can't both be Bolsa, but maybe one is. Is the maximum number of systoles always achieved on a square-tiled surface? That's, another question. I mean, it was true for the genus 1, and it's true for genus 2. Is it true for, and also the minimal strata? Is it always true? Another question I didn't put up here is the maximum systole on a stratum realized in the stratum? Maybe it's realized at a boundary, right? Maybe you have to degenerate. I doubt it. I think it's probably realized in the middle stratum. But there's nothing a priori to tell you that it's not realized at the boundary of the stratum. And then in deference to Hugo and many people who think about these things, what about as the complexity grows in the stratum? You get more zeros, higher genus. Can you get bounds on how many what the systolic ratio is, or on the number of systoles? Are there a lot on the hyperbolic surface world? There's a lot of work on this. Okay, I'm done. Thanks.